geometric mean, I wanted to give us a little bit of some shortcuts that we can use when we talk about geometric mean. So these are super common shortcuts that you might use, but you can always solve your geometric mean similar triangles without them. It's just an extra little tool that you can have on hand if you like to. So we have two rules. The first rule we're going to talk about is the altitude/height rule. Remember, the altitude is that line that we are drawing in the middle of our triangle here. Okay, so if I am missing one of these three pieces and I need to solve for it, I know that I can set up the same proportion. I'm going to show you our proportion. And then if we like to, we can just eventually skip to the final rule here. So my proportion, if I think about medium triangle and small triangle here, then I would be lining up the long leg of the small triangle, the long leg of the medium triangle, the short leg of the small triangle, and the short leg of the medium triangle. That's our standard proportion, right? It is a rule that when we cross multiply, we're going to get h squared equals a times b. And then we can square root and get h equals the square root of a times b. Oops, wrong color. So if you would like to, if you see a diagram that looks like this, and you're either trying to find the height, aka altitude, or one of those two pieces of the hypotenuse of your large triangle, you can skip right here. That formula should look familiar to you. We did that when we were just talking straight geometric mean. Find the geometric mean of two numbers. That was our formula to do so. So hopefully that is a little bit of a trick that you can choose to use or not use. The second rule that we're going to talk about really briefly is the leg rule. So if our diagram looks like this and we have one of the two legs of my triangle, either the short leg or my long leg, and then we have the hypotenuse split into two parts, then we can use this same idea of setting up our proportion and then getting to more of a formula that we can choose to use. Let's call this leg 1 here. So maybe I'm trying to find leg 1, or maybe I'm trying to find parts A or B. Then my formula will say leg 1 is the hypotenuse of my small triangle, and the hypotenuse of my large triangle is A plus B. Of my small triangle, A is the short leg, and of my large triangle, leg 1 is the short leg. So this formula looks like leg 1 squared equals A times, A plus B. And maybe you use that formula or maybe you don't, but there it is. And then the other one for leg 2. Essentially, it's the same thing. Leg 2 is the long leg of my large triangle, and the long leg of my other triangle, of my medium triangle, is B. And then leg 2 is the hypotenuse of my medium triangle, and B plus A is the hypotenuse of my large triangle. So cross multiply, leg 2 squared equals B times B plus A. So again, you don't have to use these. Some of you I know like the shortcuts, so I wanted to show it to you just in case you wanted it. But those are very common formulas you'll see when we talk about geometric mean. Good? We're going to move on. Maybe they're confusing to you, I don't know. Go ahead and flip open to 8.8. We're going to talk about something a little bit different and new. Okay, so we're still talking about the same kinds of proportions and stuff like that. This lesson just talks about, okay, well, what if we're trying to do these things with these similar triangles, but we don't have that specific diagram of a right triangle that has an altitude going through it? Well, we have a bunch of theorems that we can learn, and these theorems are not necessarily too difficult. They're all very visual theorems, I like to say, where if you look at a picture, you can set up your proportion without necessarily knowing all the specifics. The first theorem that we are going to learn is called the side splitter theorem. I do expect that you know the name of this theorem, side splitter, and it basically says, if I have a line in my triangle that is parallel to one of my bases, then it is splitting the sides into proportional pieces. So let's call these pieces, I'm going to call them A, B, C, and D. I treat that side splitter line, the thing that's in the middle, as like the fraction bar of my proportion. So let's treat this like a fraction bar. Can we see how that proportion is already kind of set up for you here? Imagine putting an equal sign in the middle. You have A over B equals C over D. That is the nice thing about these theorems we're going to talk about today, is that when you look at the diagram, your proportion should be pretty much set up for you. So this would be like A and C, B, and D. Pretty straightforward, nothing too crazy there. The next theorem that we're going to talk about is actually a corollary. It basically says, well, let's use the side splitter theorem, but let's use it when we don't have a triangle to begin with. So you're going to see diagrams that look like this, where we have a bunch of parallel lines and then other lines that intersect them. And essentially, again, these parallel lines are acting as like a side splitter. They're splitting those pieces into proportional pieces. So I'm going to take this line right here in the middle, and I'm going to use that acting as my fraction bar here. So this piece A and this piece C would go together. This piece B and this piece D would go together. Again, seeing how this is very visual, it's already kind of set up and lined up for you. Questions on that one? The last new theorem that we're going to see today is called the Triangle-Angle-Bisector theorem. It is important that we have an angle bisector in our diagram in order to use this theorem. So we're going to double check and make sure that we have those markings that say this is an angle bisector. But then from there, it's pretty straightforward. Again, I'm going to take a look at these pieces. Let's call these pieces A, B, C, and D. And if I think about my line here, I can think about it in two ways. I never like to turn things sideways if I don't have to, so I would just imagine it drawn out like that. But if you want to, you can use this angle bisector as like your fraction bar, right? Turn your paper a little bit sideways, and you can see B over C, the two pieces of that side that's being cut in half. B and C, and then the other two sides of my triangle, A and D. However you want to set it up. I just turned my paper sideways and then wrote my proportion like that. If you want to write your proportion as A over B equals D over C, that's fine too. I've basically been ignoring those little things on the side, by the way. But any questions on that? Very, very visual. It's already set up for you. You just got to look at the diagram. The last piece here that we're going to talk about is a little bit of a review. We have seen this already, a triangle mid-segment. To review what a mid-segment is, it is the midpoint of the two sides. So J and K are the midpoints. And then the segment that it forms in between those two midpoints is parallel to one of the bases. And from there, we get a little bit of a formula. So let's call this JK the mid segment. And that mid-segment is the length of 1/2 of the base. We have already seen and used this formula, but it is going to come back in today's homework a little bit, so just keep that in mind. Any questions on that? Okay, let's get into the examples. I'm going to try not to do every single example, so I'm going to skip example 1 because I think it's a little bit too easy. But let's do A and B. Here's the side splitter theorem. So I've got those two parallel lines, and this side splitter in the middle is acting like my fraction bar. So when I set up this proportion, I'm literally going to set it up the way that it is written here. X plus 1.5 over X, 5 and 2.5. I'm going to cross multiply. 5x. When I cross multiply this way, I'm going to get 2.5x plus, I think it's 3.75. Please, please, please make sure that you are distributing that 2.5 to both pieces. We're going to simplify. 2.5x equals 3.75, and x equals 1.5. If you would like to, you can always simplify the fractions that you are working with. So 5 over 2.5 might be a good example where we want to reduce that to 2 over 1 before you cross multiply to make it a little bit easier for yourself. Questions on that one? Okay, we're going to do the same thing for letter B. That side splitter is going to act as like my fraction bar. So when I set up my proportion, I have x plus 6 over x, and then make sure that we're doing the subtraction that's necessary. This piece right here is 30 minus 9, aka 21. Everybody see where I got that number? Fantastic. We're going to cross multiply. We're going to make sure that we distribute to the x and the 6 here. So this is 21x equals 9x plus 54, or 12x equals 54, x equals 4.5, and we're good there. Questions on the side splitter theorem? We got to have those parallel lines, and if we have those parallel lines, then we can set up these proportions. Let's flip it over. Now, these two problems are interesting. This says use the converse of the side splitter theorem, which the converse of the side splitter theorem is taking the side splitter theorem and flipping the hypothesis and conclusion. So instead of saying what we did in the last two problems, if I have parallel lines, then I can set up these proportions. It says, if I can set up my proportions and the sides are proportional, then those two sides must be parallel. Then that thing in the middle is a side splitter. That's what the converse says. So, if I take a look at number 3, again, that line DE is acting as that fraction bar. So I'm going to set up my proportion and see if those things really are proportional or not. So I'm going to set up 12 and 10. I'm going to set up 28 and 24. I'm going to reduce these fractions and find out, are they proportional or not? 12 over 28, I can divide both of those things by 4 to get 3 over 7. Is it equal to whatever 10 over 24 reduces to? I think I can divide both of those things by 2 to get 5 over 12. Clearly, those things are not equal. So we would say DE is not parallel to BC. That's all we're trying to say in these problems. So let's try it again with number 4. We're trying to test if DE actually is the side splitter or not. So I'm going to write this down, 9. This little sliver here, remember we got to do a little bit of subtraction. 33.6 minus 25.2 gives me 8.4. And then this guy, 27, hello? And 25.2. 9 over 29, or 27 is nice. That reduces to 1/3. 8.4 over 25.2. To make it a little bit easier for us to reduce, I might multiply each of these pieces by 10 to get 84 over 252. We're trying to figure out if those are equal or not. 84 over 252 does indeed reduce to 1/3. So I could say yes, DE is parallel to BC. Any questions on that? Okay, let's do a couple more. Oh, shoot. We have time. We're okay. I do want to do both of these. So here's the corollary. The corollary looks different to what we've done before because we don't have triangles. But again, the process of setup should be exactly the same. I'm going to start with, it doesn't really matter what I start with. I'm going to start with the x's. And I see 4 pieces that are lined up nicely that I can use for my x's. So let's literally take those 4 pieces the way that they are oriented already and make our proportion. 15 over x equals 26 over 30. This is 450. Everybody good with that first step? I'm going to fill it in. Now, because I rounded that number, 17.3, it was a number that I found, I'm just going to be safe because I don't know if I'm right or wrong. So especially if I'm doing a test or something, I don't want to use that number and then potentially get the y value wrong because I used something that was incorrect. So when I set up for my y proportion, I'm going to use the existing values, not the stuff that I found and rounded. So let's use my second proportion, which is 16.5 over 15 equals y over 26. And again, we're cross multiplying. I don't think that's 240. What is it? 429. And we get y equals 28.6. Good? Everybody see how I'm getting these? Again, I'm just looking at the diagram. That's all I'm doing. B is a little bit strange because we have so many variables. My process shouldn't change at all. I'm still going to take a look at the x's first. And I'm going to set up 5x over 8x equals 3x over 60. Now, I personally do not want to sit here and have to do square roots or factoring or anything like that. So if I can get rid of something to help me, I'm going to simplify these fractions. Take a look at that fraction on the left, 5x over 8x. What can I cancel out of that fraction? I can cancel out an x. So let's cancel out those x's. Let's get rid of them. Make my life a little bit easier. 8 times 3x is 24x. 5 times 60 is 300. So x makes a nice 12.5. That's a lot easier than trying to do some square roots business in there. So now, if I wanted to, I could fill in all of those parts, 12.5, x, all that good stuff. And then let's do the same thing for the y's. Let's see if this works. 2 options here. You could sit there and you could plug in your 12.5 and figure out what 5 times 12.5 and 8 times 12.5 is, or once again, what can we cancel out? Those x's. We're going to cross multiply. This is 80 equals 5y, or y equals 16. Any questions on that? Okay. All right. I'm not going to do all these angle-bisector ones. Let's do letter D. Sorry, I'm skipping around. Letter D. We're making sure I have these angle-bisector tick marks first and foremost. If I don't have them, I cannot use angle-bisector theorem. Then I'm going to set it up. I sometimes like to use this angle bisector as that fraction bar to help me visualize what my proportion is going to look like. So, oh my gosh. So let's split it there. Why does this look so terrible? There we go. And then let's set up that proportion. This looks like, x minus 2 over 3 equals 8 over 3x. Good? Let's cross multiply. We're going to distribute when I multiply that 3x in there. So that's 3x squared minus 6x. Uh-oh. I'm going to move the 24 to the same side. Oops. And then how am I going to solve this? What do I got to do first? Dahlia? Divide by 3. And then my factors look like, anybody? Caitlin? Perfect. I have two answers, x equals 4, x equals negative 2. What should I be checking? What do I need to double check before I'm done here? Dahlia? Let's check for extraneous solutions. So I'm going to make sure that I get no negative side lengths when I plug these things in. 3 times negative 2 is going to get me a negative 6, so I know that that's not going to work for me. My only correct solution is x equals 4. Questions on that? How much time do I have? I'm going to really quickly just do these. If you want to go ahead and get your math lab out, that's fine. I'm just going to run through these mid-segment ones, but since we've seen this already, I won't talk through it. So I'm just going to do these really quick.